So, good afternoon, everyone. We're Team Weight Watchers, and for our challenge, we chose Fly by Wireless. Um, as our solution, we created a project called A3, A380 Wireless Innovation. In our brief, we're asked to create a concept of the based on the aircraft that already exists, and for our solution, we chose aircraft Airbus A380. And the main task of our challenge was to reduce data wiring, connectors, penetration, weight, and add any other extra features.
So before we got to finding the solution, we thought we'd find the problems first. And so these are the problems we analysed. We thought there was a massively high maintenance cost with the A380 because through our research we found that the A380 has 470 kilometers of copper cabling. So when it comes to maintaining the aircraft, there's so much to go through, which requires a lot of manpower, a lot of employees, a lot of hours, and it's meticulous to get through that amount of cabling, which obviously results in a lot of costs. Obviously, the complexity of a system that large as well. It slows down the assembly of aircraft. There's a lot of projects that are delayed because of the intense time schedule that they have, where they have to do so much and so little. So reducing cabling in any way would impact both of those problems. Obviously, that also adds a lot of weight to aircraft, so that increases fuel usage, which is obviously not good for the environment. And also, if we could reduce fuel usage through weight reduction, it would affect the company's bottom line profit, which is obviously very good. And a lot of planes, due to their long lifespan, by the time they're retired, they're pretty out of date because their systems are 20 to 30 years old. So we thought implementing new systems and coming from a sort of bottom-down approach, we can work and use the newest technologies, which would not only improve the plane, but also increase its lifespan, because we would be able to use technology which is more relevant further down the line as well.
To make our solutions appropriately tailored, we split systems of the aircraft into two categories, which are safety critical and non-safety critical.
So after thorough research of all the possible solutions, we've decided to pursue four of them, which were the fiber optics, wireless sensor systems, wireless power delivery, and printed electronics. Fiber optics. So as you may know, as my colleague already said, there are 470 kilometers of copper wiring in the aircraft. Our brief suggested that we can take up to 30% of it and replace it with wireless, but we went further and replaced even more the safety critical systems, for example, with optic wiring. Well, there are some cons to it, for example, the bending, because you can't bend optic wires as you would the copper ones, but we thought that to also the durability, but where you would normally use harness of copper wires for multiple channels, you can just use one optic fiber to send multiple signals just through one tube, which is much better, I think. And also the latency is much better with the optic fibers. Even though the weight and the cost of the optic fibers is con here, it still can measure up to the copper wires thanks to its multiplexing and latency and all other pros. So we basically took the initial length of 470 kilometers of the copper wires and reduced it by 30%, which we supplemented by wireless technologies. And then we made a combination of optics and copper wires, because we also had to think of power wiring as well as the cornering, etc., which took more than 46% off the initial weight of the cables. This could lead to easier maintenance of the aircraft because you don't have to check all the lines and there is less of them. Faster completion of aircraft because there won't be any delays in deliveries after montage of the aircraft itself, and there are less technicians required to maintain the aircraft. Speaking of weight, the initial weight of all the cables in the aircraft is around 5.7 tons, by replacing it with wireless. 40% of it is taken off, and then using our combination of optics and copper, we can take additional 45% of the weight of the wires from the aircraft, which is 0.5% of the total weight of aircraft. It might not seem a lot, but it actually is. It's around $1,000 per one flight, which is quite a lot.
So another way we decided to tackle the issues were through wireless technologies, wireless systems. So we were going to replace the traditional sensor systems with a more modern wireless system integration. So we first start off by replacing the non-critical systems, such as climate control, and then as we develop the data, learn how to use technology, we'd be going more towards, smoke detectors, emergency lighting, as I mentioned, and also the engine sensing. So as we get to know the technology better, we'd be moving more towards the safety critical systems as well. But obviously with that, there's an additional worry that you have to have multiple redundancy systems, dissimilar redundancies as well. So usually on an aircraft, there's 2 or 3 redundancies for especially safety critical systems. We'd be reducing that to maybe just one dissimilar redundancy, because we would have the initial being wireless. And the big idea here was to innovate and use energy harvesting sensors in the system. So that would be done through using solar power, using the thermal gradient across the fuselage, aircraft stresses, and stuff like that to power the sensors. And basically, the diagram here shows an example where we're using solar to send a radio frequency to the autonomous sensors. They can use the radio frequency to convert that energy into electrical, which powers the sensor. The sensor then feeds to a main server, and there's communication that way. So these are the benefits and the drawbacks of the wireless sensor system. So obviously, reduces the installation of the new, more traditional systems with wires. Sensors are more, they can be easily optimized, they can be updated through software updates, just like phones and cars. There's data dumps and information that you would like from systems are much more frequent. They're much more reliable because you can get them through wireless networks rather than having to dig through the whole thing, do the whole maintenance thing. We have to take apart plane, organize the whole ground staff, meeting, get employees on the case. You can just do it through your tablet. And as a chief engineer or anyone in that position, it's much quicker. It's much more frequent as well. But obviously, the drawbacks being wireless, there is signal interference. So to tackle that, we would be using different bandwidths, or as soon as we encounter interference during flight, for example, there would be an automatic system which would change your frequencies or do something of the sort to encounter the interference. And obviously, the power issue where the sensors would be very energy limited. So those would be technologies we'd have to research further into and get maybe industry help to develop even further.
We have 2 ways of delivering power wirelessly, and first of them is leaky feeder, which will be installed in the center of the fuselage between 2 floors of A380. It will be delivering power to the laser transmitters, about which we will talk on the next slide, and also to the other non-safety critical systems. It actually has dual purpose. Second is to deliver information to status lights using VHF and UHF frequencies. So our second way of delivering power wirelessly is power beaming. It will be delivering power to in-flight entertainment systems and non-safety critical systems. Yeah. The way it will be operated, there will be laser transmitters installed on the ceilings of cabin floors that will be sending laser beams onto photovoltaic cells that will be installed on the devices that require energy. And advantages of this technology is that it can transmit energy over large distances, has no interference, and very minimal power reduction. big challenge faced by latest technology is overheating. Uh, however, there are two ways to solve this problem. First is using artificial diamond lasers, and second one is to use pinpoint precision technology.
Lastly, we had a look at were printed electronics, which could also serve as power conductors or as sensors, for example. So they would usually probably get data from the leaky feeder itself and power from the laser bulbs. The good thing about printed electronics is that we might be actually able to predict maintenance date and schedule it, so not to have delays in flight departures, etc. So the technicians would actually know when the tank is going to fail because they would have statistics about it, or when the sensor is going to stop working and when they have to come and repair it or check it. The good thing about printed electronics is there is a good way of redundancy because we can use composite layering. So we would have one layer of composite, one layer of printed electronics, another layer of composite, another layer of printed electronics, and this way we could have less penetrations throughout the aircraft because we could actually use, for example, the bulkheads or the floors as a conductor. So about the savings, how much do we actually save by replacing the cables in the aircraft? We calculated that by replacing the copper wires with fiber optics, we can save up to 45 or 46% of weight of cables. Also using the wireless technologies, we can save the 30% of the weight of cables. Then the wireless power using the bulbs and the laser technology, we can save up to 4% of the weight of cables because we wouldn't need to power every device by cable. We would use the lasers. And also by using printed electronics, we estimate that we would save up to 2% of weight of cables.
So overall, we find 1% weight savings of the overall weight of the aircraft, which is about 570 tons, which may not seem a lot, but if you calculate it the way we have here, so which is $1,200 per flight, times that by 300 A380 flights, which happen on the daily, which is 260,000, times that by 75,000 flights, which is the amount of flights over 250 days, which is an active number of flight days for an A380 in a year, which results to about 90 million. And then average lifespan of 25 years, which gives you a grand saving of $2.25 billion with 1% savings on our fuel. So that's where we think the biggest impact is. It's not like a one-hit solution. It's an over time saving, which the company can then reinvest, and yeah. So that was our project. We had some additional ideas as well. It was just throwing these out there. This wasn't anything too serious, but this is future developments that maybe we could also incorporate. So this was solar panels, maybe printed solar panels on the roof, for example, something like that. Morphing wings as well, which is obviously very hot in the industry. That would not only reduce drag, but also less moving parts. So again, maintenance goes down, and stuff like carbon nanotubes as well for cabling. It's very lightweight, very strong, but again, very concept-based at the moment. And then some smaller ideas that we had with like touch screens and with haptic feedbacks in the cockpit to reduce switches and cabling there. Luminescent lighting instead of dim lights, so just having a passive lighting panel on this roof of the plane. And then a big one that was the laser-based power transmission. So something like the solar sail, where there's lasers that power the sail. You could have something like once the plane is in cruise, you can have lasers from either satellites or ground stations that transmit power to the plane, combined with the solar panels on the roof. That could provide a substantial amount of power, which could power low-level circuits and low-level systems as well. So those were some additional ideas that future concepts could even incorporate. That's our presentation.
Yes, please.
Thank you very much. nowadays, security is a big issue.
Yes.
How you, because we know the fiber optic is mostly the wireless,
Mhm.
and we have concept of security.
So we designed the fiber optics for the safety critical system. So anything that the pilot controls or any control surfaces, that would all be cables. The wireless would be for any non-safety critical stuff, so maybe in-flight entertainment or light controls on the roof and stuff. And obviously with any wireless stuff, as it gets more towards the safety critical system, there'd be high levels of encryption and the safety measured in that way. So anything that would be non-encrypted would be very low level, which will affect the performance or safety of the aircraft in any way.
Which of the massive challenges was this?
This was the fly-by-wireless. Yeah.
In terms of cost savings, obviously fiber is more costly than copper.
Mhm.
Have you put into that consideration?
Yes.
And are you in the process of doing it?
Do you take that?
Yeah. So as we said, we can replace the big harnesses of copper with optic wires, and we try to find kind of a harmony between copper and optics. So it doesn't cost more than it would normally for the copper. So as you may know, the optic wire can carry up to 3 signals, I think, or something like that. So normally when you have copper wire, it's either 0 or 1, but when you have optic fiber, it's more than that.
So basically, for an equivalent copper wire versus fiber optic, you'd be able to carry way more. So it may cost per unit more, but when you factor in the amount of data you can transfer, it's way more cheaper to use fiber optic.
Yes.
What did you decide what was essential? When deciding how much you save in money, what did you decide, like for example, the lights, what did you decide that was essential in order to calculate the cost and how much you're saving instead of removing the cables?
So it was basically the initial decision was safety versus non-safety critical systems. So anything that the pilot needs to control the aircraft was considered obviously safety, and non-safety would be anything to do with in-flight entertainment or lighting or stuff like that. And so obviously we don't want to put the safety of the plane in jeopardy. So that would be all wired connections, as I said. And that's how we kind of went around it. That's your question.
Yeah, it's more of a, for example, lighting may be an essential thing. So if you take that into account, that it's not, you're removing a big part of the cost, so it might not be 1%, it might be 1%.
So
I'm just saying that it varies what you define as essential in the plan and what you want to remove.
like, I don't get what
I
the
don't know
question
if the question, or was it a question?
The question is, what do you define as essential and what's taken away?
What do we define as essential?
Yeah.
Yeah, so anything that's considered a safety system, critical safety system, is essential, which we don't want to play with. And then there's anything that's non-safety, non-critical safety systems would be the non-essential. And that's like industry standards. There's specific things that are safety, and specific things that aren't. So that's how we decided. We just looked at the industry standards.
Yes.
Okay, once having wireless, there's some loss. And how can you calculate the loss and the gain of the data when transmitting? Because there's some interference in the wireless. You calculate what that?
So
Yeah, so we obviously thought about the interference. So there would have to be different sections of the plane where we would actually make use of bulkheads, which may in other case be bad for us, but we may use them to stop the interference as they would block the signal. So we would have different sections of the plane so that the sensors and all the wireless technology wouldn't interfere that much. Also, we would use the different frequencies and bandwidths to make it as efficient as possible.
What protocol do you use? Protocol.
What protocol?
Yeah,
As in,
wireless. Something like example sensor.
yeah, we were talking firstly about the leaky feeder, which would use normal, very high frequencies and ultra high frequencies. Then we were thinking also about using Wi-Fi. So I don't know what protocol is that, to be honest with you.
Because when you're sending data to wireless, you have to know what channel you're using, and because that's you calculating how many data you transfer, how
Yes.
much you can get in the end again, and that's very important to
Mhm.
know what's the protocol.
We would have to make more research about that and look into it. I guess.
Sorry, we've had too many questions. Can I just get the principle right? So essentially you're replacing a number of copper cables with one fiber cable, is that right?
No, no. So there would be multiple fiber optic cables. There was what was the exact length?
It was 1 kilometer, I think, for fiber optics, which with the length of 73 meters of A380, we could go up to 360 lines which would go through all the plane. So we can make 360 from the cockpit to the tail, basically.
Essentially, let's say 5 cables, one for the lights, one for the aircon, one for the landing gear, so 3 cables. You're replacing all 3 by one.
No, so there'll be different cables, and the way we kind of imagined it would be sort of like an artery system, where there'd be a main cable of fiber optics, and then that branch out into smaller copper cable to feed into any different system. Because obviously we can't bend fiber optics around top corners or anything, so that would be the job of the copper cable. But there will not be a single cable, because obviously in terms of redundancy we wouldn't want that. So it would be multiple copper fiber optics all over the fuselage basically, which would we had a diagram to show as well. Which is one across the length.
Yeah, we tried to illustrate it here in this diagram, where you can see the black lines are basically ones we added, which could potentially be the fiber optics. So there won't be just one line, because if that would get damaged, you lose control of the plane. So
That's what I'm trying to get to. You've got a single dependency on one.
yeah, it's not dependency, just on one. Yeah.
All right.
Okay.
Thank you very much.